We've been talking about flattening the curve, which is the process of reducing this maximum number of persons that would ever have to be infected at a given time during our epidemic. And that would reduce the number of people who are ever hospitalized at a given time, the maximum number, and allow for our healthcare system to function well. We saw that flattening of the curve was really determined by changing the R0 value that describes the epidemic. The R0 value is a dimensionless ratio of the characteristic recovery time over the characteristic time required to spread the infection due to community spread or interaction. And so by reducing that R0 value, we get a recovery time that's shorter and an infection time that's relatively longer, and we end up with a situation where not as many folks are infected at the same time. Last time we also discovered that a very simplistic approach to talking about epidemics would at least reveal something about that infection time. And that was that in this simple model, the rate of change of the number of people who are infected is determined simply by one mechanism. We called it community spread or interaction. It's where the interaction between those people who are uninfected and those who are infected causes the number of infected people to go up. Alpha here was a positive parameter that we wanted to get more physical understanding of in the problem. And to do that, we basically scaled the problem. And we ended up with a very simple, dimensionless, scaled universal ODE. What it means to be simple is that this equation up here, originally this system, it had three parameters, alpha, n, and y naught. The scaled problem only has one parameter, epsilon, which is, in fact, the initial percentage of individuals who were infected. So that's one reason to do dimensional analysis. We get a simpler ODE. The second reason to really do dimensional analysis is that it helps us to focus on particular mechanisms in the problem, and we'll see that today. We'll also see it here when we review. The last reason that I want to mention before we go on, though, is that by scaling the numbers, we can really allow our scaled values to go into a nice range. So for instance, y goes between 0 and the number of people in the population, which can be quite large. But y on n, the total number of people in the population, goes between 0 and 1, because now y star is just the percentage of the population that's infected. So by scaling the problem in an intelligent way, we really get a range of values for our variables that can be very helpful. The computer oftentimes has difficulty working with numbers that are very big and very small in the same problem. It has two types of error, truncation and round-off error, and so the loss of significance that can happen when we're trying to work with problems that are not well sized is severe. And so by scaling the problem, we can kind of resize the numbers so the computer can work with them well. Whereas we had a really good guess on what to scale y by, t we didn't really know what to scale by. We instead decided to allow the problem to select it for us so that we could see the effect of community spread. The way that we did that was that we allowed for t to be scaled by an unknown but constant and characteristic value called tc. Once we substituted in for y and t in terms of y star and t star into our differential equation and in terms of the ODE, by simplifying the differential equation and the initial condition, once we simplified the initial condition, we got the parameter epsilon. But simplifying the ODE such that we had divided through by the coefficient in front of the highest order derivative here, such that we now had a differential equation that was dimensionless, where the change term is weighted by a 1. So this derivative term is really talking about how change occurs in the problem, and it's got a 1 weighting it. The only mechanism that's equal to that is the mechanism of community spread. So if we'd like to see community spread affect the change, we want to go ahead and weight it also to be a 1. The change of individuals who are infected. So if we want to weight this to be a 1, we certainly can do it because TC was undetermined. So by selecting TC to be 1 on alpha n, we ended up with a weighting of a 1 in front of the community spread term, and that's really what alpha is. Alpha is the number that when I take 1 on alpha n, I get the characteristic time needed to see community spread affect my population of infected individuals. So we also did a little bit of dynamical systems analysis last time, but here what we really want to do is solve this really famous, this is a famous differential equation. Once we've scaled it, it becomes really clear. This is what's known as the logistics equation. So we could actually compute an exact solution to it, and that would allow us to compute an error. What we really wanted to do, though, is solve it on the computer numerically using explicit Euler's method, which is a very simple method, but really the root of more complicated ones. And so it's really important to understand. It really comes from just running the forward difference backward, if you will. And so we ended up solving the forward difference operator for y plus 1. What that means is that the solution at the next time step is related to the solution at the previous time by a linearization, where I take the slope, which is known because we are solving an ODE, so the slopes are given to us, where the slope at the initial point multiplied by this run would give us the necessary little bit of rise to get us to the next solution. And so this would allow us to hop from one solution to the next and really reestablish this curve of what y would look like. And so here what we're going to do is consider a simpler model where not everyone ultimately has to become infected, because not everyone does. The SIR model has 3 bins in which our population is divided. X is going to represent the number of people who are susceptible to the infection. Y is the number of people who are infected and actively giving off that infection, so to speak. And a new bin, R, is going to represent the number of people who were infected but now have recovered, and so are no longer causing their spread of the virus. As before, we're going to take the total number of people in the bins to be a constant, the total number of persons in the population. And so if we look at this now, we're going to actually have, for instance, in our equation, differential equation that describes how y changes, there's actually 2 terms. There is a term of community spread, which is positive, and so this term is going to cause the number of individuals who are infected to go up. The mechanism of community spread does that. Whereas the mechanism of recovery, which is really determined by taking a portion of the infected people and allowing them to recover, that group is going to cause the number of y people to go, or of infected people to reduce, and so it's negative. And then, as you might think, that number of folks is actually how much r goes up. Whereas the number of people who become infected are then moved out of the X bin, and so this causes the number of people who are susceptible to go down because now they have become infected. Each one of these ODEs is supplemented by its initial condition. We have an initial number of persons who are infected. The initial number of people who are susceptible are n minus that initial number of persons who are infected, and initially we're going to assume that there are no recovered individuals. X plus y plus r is a constant n. So if we look at each one of these derivatives and add them up, what we'll see is that the sum of the derivatives is, of course, the derivative of the sum, where that sum is a constant, and so the derivative of that constant is 0. That means if we add up all these guys, we should get a 0, and that's what we do indeed see. Dx dt, dy dt, dr dt summed is just 0. So this seems to be a model that would conserve the total number of persons in our population. Let's scale it. Again, we scale all of the values of persons in the bin, a bit different bins, by the total number of persons in the population, which makes them go between 0 and 1 quite nicely. But we'd like TC to be determined for us. So we're going to substitute, as we did before, into our differential equations for x and t, y and t, r and t. Here are the new differential equations, where we're going to bring out n and tc, which shows up in every single one of these differential equations on the left-hand side. And that is going to be n on tc, that is going to be the coefficient multiplying the derivative. We're going to go ahead and divide by it. And so multiplying through by tc on n, we end up with dx star dt star is going to be equal to minus alpha n tc x star y star. Similarly, we're going to end up with dy star dt star is equal to alpha n tc x star y star minus beta tc y star. And then lastly, dr dt star is going to be equal to beta tc times y star. Again, the change terms are all weighted to be by a 1, so 100% of them is, so to speak, visible. What we really have to determine now is which one of these mechanisms we want to focus on, because once we've determined TC from any one of the mechanisms, either the purple highlighted community spread mechanism or the recovery mechanism. Once we select that, it's going to determine a parameter for the other mechanism in the problem, as we'll see. So let's consider the two possibilities. We could either weight the problem so that recovery is visible, so we had a 1 here and a 1 here. That would make TC equal to 1 on beta. That would cause this to be a 1, obviously. This would be a 1. But now the number sitting out in front of the community spread mechanism, alpha n times TC, would now be alpha n on beta. And that number would not be 1, not necessarily be 1 at all, alpha n on beta, again up here. We could, on the other hand, choose to force the problem to resolve for us in terms of change the effect of community spread, in which case we would choose TC to be 1 on alpha n. That would cause this to be a 1 and this to be a 1. But now we'd have beta on alpha n multiplying y star here for the recovery effect. And we'd have, again, beta on alpha n here times y star to be this recovery effect. So we get to pick one or the other, but once we've picked it, we have to be consistent in replacing TC. We typically choose to focus on the recovery mechanism. And if we do that, replacing TC with 1 on beta, we end up with this very simple, system of first order dimensionless ordinary differential equations, where really we can see there's only 2 parameters left. Epsilon is still hanging out, just like it did in the previous simple model, but now we have another parameter, alpha n on beta. And in fact, alpha n on beta is none other than the R0 value. So 1 on alpha n is the T infection time, and 1 on beta is the T recovery time. So this is exactly where we get this R0 ratio that people are speaking about. And it's important that we understand that R0 is not saying in a simplistic way how many people every other person is going to infect, because the rate of infection changes with time. It's not a constant. What is constant is this characteristic recovery time over the characteristic time of infection for the epidemic. So we can go ahead and once we've scaled these guys and we've replaced alpha n on beta with the single parameter R0, we get our very simple system of differential equations where there's only 2 parameters, R0 and epsilon. We can also see that dy star dt star is going to there's going to be a 0 derivative, or that y star would peak whenever we would have R0 times x star minus 1 quantity times y star equal to 0. So wherever the derivative vanishes, y star, the function, is going to possibly peak. So that would happen when, when y star is 0, that's a spurious answer, because y star being 0 would be there's no infection, so no epidemic. X star is when we'd have 1 on R0 being equal to x star would also cause this to be 0. So obviously x star is a percentage, it has to be less than 1. And 1 on R0 would be really that amount x star of individuals who are susceptible where we would experience a peak. So what that really means is that R0 in this case is going to be bigger than 1. And it also means in that case that the T recovery time is bigger than the T infection time. And whenever that is the case, we can expect there to be a peak of y star. And indeed, we could show this rigorously by looking at the second derivative and seeing that it is a negative number. And so the slope of the slope is decreasing, or it's concave down. And that would cause this to be a maximum. Anyway, we now are going to take these differential equations and solve them using Euler's method. It's a little different because now we have to solve them all together simultaneously. And that's because the derivatives depend not just on x or on y, they depend on x and y always. And so in order to compute a derivative at any location, I have to know x, y at those locations. So what that means is that I can't just solve for x, all the xi numbers, xi plus 1 given the xi numbers, we can't just solve all of those separately from the y and the r values, because really the y values show up in the derivatives. And we'll see that in the next slide where we see the solution mocked up for us in MATLAB. But really what this is saying is that if I'm given a value for x, y, and r at a given solution, from those values I can get the next values, x at I plus 1, y at I plus 1, r at I plus 1, all starred. And then we repeat the process. So if I is 1, we can get I equals 2. If I is 2, we can get I equals 3, and so forth. Here is the very simple, basically a repeat of our previous process, where we've got a loop where we roll through in order, getting each one of the values of x, y, r of I plus 1 from the x, y, r values at I. And here we've just plugged in the derivatives, multiplied by the step sizes. Some of the derivatives are negative, as we saw. So don't be surprised by that. Some of the derivatives are negative. And once we've gone through this process and looped through, we can take a look at the solutions. So let's do that real quick. This is for r not equal to 2, an initial epsilon value of 0.01% of the population infected. What we can see is that as things progress, the blue line is the susceptible individuals. It starts out at almost at 100%, whereas the red line is the number of infected people. It starts off at almost 0, and R, the number of recovered individuals, is 0. So as time progresses, the number of susceptible people decreases because they become infected. But at the same time, some of those infected people begin to recover. And what that ultimately causes is that at the end of the cycle, we will see that not all of our individuals have actually become infected. In fact, when we're finished with this, about 20% of the folks, if R naught were 2, didn't receive, weren't exposed and infected. That's what this means. So it's not true that everyone will be infected. If the R naught value is kept small, not everyone will be infected. And the number of persons recovering, of course, grows, and the number of persons who are infected ultimately diminishes down to nothing. And so this is the curve that we were talking about, where we're trying to flatten. If we just look at it all in isolation, here it is. This is the curve, percentage of the population that's infected, as a function of the dimensionless time, which is t on t recovery. What happens if we look at a different value of R naught, say an R naught value of 5? It's a massively different dynamic. First thing to note is that the blue susceptible curve goes to 0 practically. And what that means, if R naught is high enough, everyone gets infected. Over here, if we have a certain percentage of the population that really shouldn't get infected because for them it's deadly, we can afford that and it will occur. We can actually prevent those people from getting in trouble from herd immunity. Over here, everyone gets the disease. And so ultimately in this model everyone recovers, but we know that in reality not everyone would recover. We can see that they sum up to 100% as they should, and we can see that this peak of the number of persons who are infected is much higher than it is over here for the R value of 2. And so we end up with these two separate curves, and the curves are a little bit beguiling because they don't tell you the entire dynamic. It's true, this curve is lower than this curve. What's not clear is that by spreading out the infection time, so to speak, and making R naught a smaller number, we actually save some people from getting infected. And that means that the area under these curves is not exactly the same. So going back to our initial answer, this is really doing what it means to flatten the curve in terms of an engineering analysis. And my hope is that you would be able to articulate some of these results to others when it becomes more difficult as time progresses for us to really maintain some of these good social distancing practices. The longer we can make this infection time, the better we will survive. The R naught value will decrease, and people who don't need to get infected cannot get infected. But if we make the R naught value large by disregarding social distancing, by pretending there isn't an epidemic, everyone will get it. And it will cause people who don't need to pass away to an early departure from this life. So going back to our engineering for the common good, we really have to understand what these models mean in order to do a good job of being engineers and to living out that vocation for other people. We have to have this picture, but we have to have a bigger picture. And that means being able to articulate this in a way that other people can understand it by understanding the context of their lives. Social distancing is very, very challenging. It's psychologically hard. There's a lot of anxiety involved. What we need to do is be really not just aware of those realities. We need to really be able to speak, I think, from our faith into those points of view, because science doesn't get you to a human answer. At the end of the day, you have to be able to allow people the process to really, I think, encounter Christ in a situation that seems quite miserable, and to recognize that there's real value and meaning in the way that they live this time. And I think that this is hopefully one of the ways that this time will be valuable and meaningful to you, is if you're able to live out this understanding and really be able to allow other people to appreciate it as well.